Today I want to talk about pipelining. It's a very important strategy in hardware design. Here is, actually, yeah, can anyone tell me what this kind of looks like? What does this look like? Taken in the class that this slide is like tipped and directed out. What is this? Yeah.
Five-stage pipeline.
Sure. So pipeline probably for, yeah, like a general processing unit, maybe like a CPU. Sure. RISC-V core, yes. You can see it as ALU. You can see, yeah, so there's multiple stages here that are separated by flip-flops. Okay. Why do we pipeline things? No.
Fast.
Yes. What is it?
Cycles, clock cycles.
Clock frequency, right? Yeah. What we could do, what we absolutely could do, is we could take out like every single one of these flip-flops, and I guess maybe we could just keep this like program counter flip-flop, and now it'll just like count up and up and up, and we, in one single cycle, we go and perform all of the execution for that one cycle, and we go to the next cycle, and then it does all of the execution. The issue is that what will happen is, like, if we had gotten rid of all these flip-flop stages, what will happen is the data will become like okay, boom, clock edge. Now, clock edge data comes out of this, out of the program counter flip-flop, and then goes into memory, and then is decoded out, and will like propagate through. We'll go through the register file, propagate through. We'll go through the ALU, propagate through into the memory. Well, as soon as it's propagated through, now that hardware is no longer being used. Like the second that we've done that bit of calculation, like the second that we send some data into our ALU, and the ALU performs the multiplication or addition or whatnot, as soon as we're done with that, now the ALU is just sitting there, and there's no transistors that are oscillating and, yeah, calculating some new data. And so what you have is you actually have a bunch of like hardware modules that are sitting idle for a large part of your clock cycle. So what we can do instead is put in all of these pipeline stages, and now potentially we can run our clock maybe like 5 times faster. And actually, you know, our CPU won't run any faster, because like if I you know, pass in like, okay, so I have a D side going into my PC, then okay, my receive pause edge, now the data is going to flow through, going to go through memory, and then it still needs to like arrive now at this point. Then we wait for another clock cycle, then it goes through, and it goes into the register file, and then get another clock edge, now it goes through this flip-flop. So our CPU isn't actually running any faster, like the latency, the time it takes for the program counter to change until like the now data has been successfully like written back into the memory. That like time is not going to be shortened at all. But why is it that pipelining is still useful? Like, why do we pipeline things if it's not actually going to speed up like change our latency? Yeah.
Because it reduces strain if we just use like one.
It reduces what?
Like strain if we just use one instead of like without it.
Strain. What do you mean by strain?
Actually, no, I don't know what I'm talking about. I haven't taken much study yet.
Okay, no worries. Yeah.
It allows you to parallelize by basically starting to work on the next operation while the current operation is still being done.
Absolutely. Yeah. The whole idea is parallelism. You can think of it as like an assembly line. Now, instead of just looking at one single bit of data, instead of just looking at our program counter and now the data going through, and then it's like, okay, now it's running this instruction, and it's performing the ALU, then it's writing it back. Well, in that whole time, we actually, like, as we run one instruction, then the next instruction will also begin working. And yeah, the next instruction program counter will be fetched, and then on the next clock cycle, now like the second program counter's register file registers will be fetched. At the same time, now the program counter is incremented again. So what we're going to have is every single one of these hardware modules is going to be utilized more often. You're going to have like more of your hardware that is actually doing work, because yeah, now your stage, you can think of it as like your pipeline stage is shorter. So there's less of a distance for combinational logic to need to propagate through. And so therefore more things can work in parallel and be synchronized. Yeah, because like, in theory you could have maybe like 2 signals propagate through, like you could send like a signal through like a combinational adder, and you could wait for it to propagate through all the wires, and then maybe like right as it meets the midway point, maybe you time it perfectly to where you send out like another bit of data, and then it propagates through. The issue with that is it's not very consistent timing-wise. But by putting flip-flops in, you like segregate off each pipeline stage so that all pipeline stages are now perfectly synchronized. There we go. So things become synchronized, and now you can treat it like an assembly line, and there's more parallelism. Yeah, Marco. And it also increases throughput. Yeah, because now you like if you think like we're adding in like a new instruction, if we're running an instruction now every maybe like every like 5 nanoseconds or something. So every 5 nanoseconds we're running an instruction. Well, that means that at the end we're going to be also like receiving instruction like write backs every 5 nanoseconds as well. And potentially, like if we didn't have all of these pipeline stages, then maybe that would be closer to like 25 nanoseconds, because those instructions couldn't be doing work in parallel with each other. Yeah, absolutely. Okay. Maybe we are experienced seeing like flip-flop structures like this, where maybe you have like a single flip-flop and then a combinational stage, and then flip-flop and then combinational and flip-flop combinational. Have we seen this before? Since in 120? Okay, sure, cool. Well, this actually can be expanded out to ready valid as well. And there's a good diagram, here, this is fine, sure. So here, imagine that each one of these are modules, maybe it's like a multiplier or adder or something, and the idea is, maybe this internal module, maybe it's pipelined, maybe it's something else, maybe it's a FIFO, but importantly, it has a ready valid interface. So on the consumer side, it will have ready and valid, and then on the producer side, it will produce some sort of output, and then it'll send it out, and then that's sent into another module. And if we wanted, what we could do is eliminate all sort of pipelining, and instead we could just say like, okay, when all of these stages are done, then we would say like, then our front I/O is now ready to receive more data. So when everything is done, we're ready to receive data. But if we pipeline it instead, then what we can say is like, okay, well, just if our first module right here is like done with whatever it's doing, then we can say it's ready. So we can have our first module here say that it's ready, even while other stages later on are also working. Cool, okay. So now, what happens if maybe we have this first module is really, really slow? Okay, so maybe it takes in something, maybe it's a really big like multiplier, or maybe like a sinusoid calculator. Let's call it a multiplier. So maybe we have this really slow multiplier that takes like 100 cycles or something. And then everything past that, maybe it's like really simple like adders or XORs that all take like 1 cycle. So what would that kind of look like? Let's say I wanted to feed in a bunch of data. Let's say I had like 100 things that I wanted to send through, and my first thing was very slow. Okay, go and chat with the person next. You kind of explain what that would kind of look like. Like where would the clogs be in each stage? Like would we ever have like things where things come in and then stop in certain stages? So I'm asking, so if this first one is very slow, but everything else is really fast. What would this look like? So let's say we have, maybe like 100 things that are all pending right here. So there's data coming in, so data, right? Well, since we have this very slow first module, now this data is going to be stalling, specifically whenever this first module is working. And then when this module has finished processing like the first bit of data, then it will send it out to this next one. And we can imagine that probably this next module, because like the first one was so slow, we can probably imagine that this output is already going to be ready to receive the next data. And then if all of these are fast, maybe if they're all like roughly take the same amount of time, then we can imagine that the data will just kind of like go without stalling into each of them. Yeah, okay. So this is if we had like slow and then fast. Well, so now what would happen if maybe we have it kind of like reversed? So maybe like these are all fast, but then we have a slow stage at the very end. So in this case, okay? So in this case, we would probably have maybe like, I don't know, some amount of time where we can take in maybe like 3 whole bits of data. So we take in 3. thank you. So we take in, yeah, maybe like here's 1, and then 2, and then 3. And then finally, then we go and we take in a fourth value here, so now these all move. But now, all of these, since they're fast, now they are going to be waiting on the slow one. And so now, unfortunately, things need to stall. And it's specifically because of this stage right here. So ideally, when you have a pipeline, in general, like when you have like flip-flop pipeline stages, you want to even it out to where every stage takes roughly the same amount of time. And that also goes for when you have a pipeline stage with like producers and consumers, with ready valid interfaces. You roughly want each kind of stage to take the same amount of time if you're using modules with ready valid interfaces. It's kind of, yeah, the exact same thing. Okay, good. So, okay, yeah, maybe a question now is how would you actually, let me see. Yeah, this is good. So if we think back, yeah. So if we think back to probably, yeah, like 120, 220. So if you're implementing a CPU, like a 5-stage pipeline CPU, right, and maybe you had to stall in like the ALU stage or something, then what would you probably do? Like how did you implement stalling logic when you had to stall a flip-flop stage? Okay. Yeah.
It's just a guess, but could you like no op for like a few cycles?
Yeah, that's possible. So yeah, any other ideas? Yeah, Albert.
So also yes, you have to write like whatever is like stalling, like that data to like somewhere else.
So usually what happens when we stall a pipeline is, so there's not like any sort of like ready valid signal, like on a single flip-flop is not going to have like a yes, I'm ready to receive data, or no, I'm not. So what needs to happen is if you had to stall on like the ALU, what you will do is you will create like a kind of global net, maybe your ALU like module in Verilog has like a stall signal, or maybe it's just a ready signal, and you send that out to all previous stages, and you like it's an explicit wire that's like, please do not take any more data. And this wire would be sent to the previous stages. And this is how you would do it if you were creating like a processor where you had each stage be a flip-flop like this. In a ready valid interface, when you have it instead looking like this, what's really great is implementing stalling is just kind of given to you for free. Because now you don't need to say like, hey, like if I'm really slow right here, like usually maybe you'd be like, yeah, like, oh, please stall if, like, yeah, maybe this is like a global signal, stall. Maybe this is advertised, everything else, and it's like, yeah, please do not send any more data. Like, I can't receive anything. That is what usually would happen in like a CPU. But instead, what would happen is if we are stalling, then we would send out a like ready equals 0. So I'll say, yeah, I'll say n ready to denote that we are not ready. Well, then this not ready is also going to be back propagated just by default for free by the previous module. And then will also be just, for free back propagated as well by the next module. And then back propagated again. So ready valid interfaces like work just extremely well, just out of the box with pipelining. And that's like a huge reason why we love ready valid interfaces, is because you can just like hook them up together, and now you have like a huge pipeline stage just for free that implements the stalling logic for you automatically. And you don't need to like account for the edge cases where it's like, I want to stall in this case, or I don't want to stall in this case, and have to create like some big combinational thing. Instead, you just use the ready valid signals like normal, and what you'll find is that when you are working and you are not able to send the data out to the next module, then you say that you're not ready. Yeah, Albert.
Can you explain how to like back propagate?
Sure, okay. So let's say this module is currently working right now. So if this module is working right now, then it would send out to the previous module that it is not ready because it is working. Well, now this module, let's say that it is done producing data, so the data is valid, but it sees that the receiver is not yet ready to receive that valid data. So since it's not able to send out that valid data, it needs to stall until it is able to send out the valid data. So it's going to say, I'm not ready to receive anything new. I need to wait until my next stage is able to receive something.
Okay.
Yeah, and then it keeps going. Yeah, down here, it's going to say like, oh, I'm sending out valid data, but is my receiver ready to receive it? It's going to say, no, I'm not ready, so it's just going to stall. Yeah. Yeah. Cool. Yeah, and this is like a great thing that just like, it's very satisfying when you take all of your like, a lot of IP will use ready valid interfaces, and it's very satisfying to just like link them together like this. Because you don't have to write like any Verilog, you don't have to write a state machine, you just instantiate all these modules and then just hook them together, and now you've created like a pipeline for yourself automatically. Yeah. Okay. And yeah, question?
What kind of these sort of intercommunication systems are used in modern processors? Do they use something like Ready Valid, or do they
Yes, absolutely. Yeah. Ready valid is a overarching term to describe like basically every single parallel communication interface uses some variation on ready valid. AXI, the like ARM or the AMD, whatever extensible interface, whatever it is, AXI uses exactly ready valid. There is Avalon, which is something, it's like wait for stall or something and then ready, but it's basically just ready valid. And then there's Wishbone, which is also just ready valid. Yeah, so there are like big documentation manuals that describe specific communication protocols, but they also all basically just boil down to ready valid when you're doing on-chip communication like this. Yeah, cool. Good. So let's see. It's fine. Yeah. Okay. So I guess now the question is, what would happen now if? I'm gonna actually bring this to a new slide. Okay, let's say we have two modules right here, and maybe these two modules, maybe they're taking in like, I don't know, two like addition operations, so, or maybe they're taking in an addition operation, and then they produce some sort of sum, which then goes into some like multiplier on like a some later stage. Okay, this can absolutely happen where maybe you need to send in two operands into some sort of module. Yeah, if you have a multiplier, it will take in operand B, operand A, operand B, and will maybe take them from two other modules that have a ready valid interface. Okay, let's write out exactly what ports we have. So let's call this A, let's call this B, and let's call this C. So A, we'll use like the dot operator. So if we say A dot valid O, and we say A dot ready in, and we have B dot valid O, B dot ready in, and we have C dot valid in, and C dot ready. And let's assume that maybe the data pins have already been connected properly. So maybe there's like some sort of data that comes out of here, and then data comes out of here, and maybe that's already connected. So now all we need to do is go and connect all of the ready valid pins. Okay, well, we have a slight issue. The slight issue is that we can't just like connect that to that because we don't have like a one-to-one mapping anymore. Okay, what do we do in this case? Think about it for a minute, discuss with the person next to you. How would you connect these 6 pins to each other in a way that would make this work in a similar kind of manner to like how I showed you, where you can still like have like, you know, back propagation of these like ready signals. Okay, yeah, think on this. Any thoughts? Strategies? Okay, Ollie?
Well, you could use an AND gate from the two valid outputs of A and B that connect into the valid input of C, so it only executes the operation once A and B are valid, since
Sure.
you need A and B.
Yeah, I like that. Okay, so notice that, yeah, we have A and B here that are both trying to produce valid output. So when they're finally ready to receive, or sorry, when they're finally, yeah, outputting valid output, then only in that case, when both A ready, sorry, when A valid and B valid, so when both of them are true, then in that case, then we can say that C input is valid. So absolutely, so when we go and assign C valid here, we would probably want to set this equal to, yeah, the two valid signals. Okay. Do we have thoughts on ready? Okay, ready? Someone else? Ready? How do we get ready working? Okay. Eli? Yeah, I think we can just connect it, right? Because if C is ready to receive data, then yeah, it'll tell the sides. Yeah. Okay. So. Yeah, let's say it's equal to C ready. And then B ready. Yeah, absolutely. Okay. Good. Do you know what I'm going to ask next? Okay. What if instead we have maybe a multiplier producing a product, and that product needs to then be used by 2 more modules later on? So I'll go and draw that out. Yeah, so now we have this structure where maybe this the C is now producing. Actually, I'll also rename these. I think that'll be better. So this is A, B, and C, and A is producing data for both B and it's producing data for C. Okay. Maybe go and either write it out or type it out. Right now, like what the Verilog description would be of this proper connection here. Yeah, you might need AND gates, OR gates. It'll be kind of similar kind of style to this. And actually, I'll leave this up just for your inspiration. But this is not, it won't be this, but it'll be similar. Yeah. Yeah, Albert?
I would order the two like ready values.
Okay. So you're saying or like B out and C out, right?
Yes, yeah, ready.
Okay.
And then I'd feed that into A.
Okay.
Because from my understanding, it
Yeah.
shouldn't matter which one gets it first.
So let's see. So we have, I guess, yeah. Yeah, so we can say, so A ready in is equal to, you know, B ready out. You're saying OR with C ready out. Okay. Do we agree with this? So, okay, so let's say that A is, you know, sending out valid data. Okay, sending out valid data. Let's say B is ready to receive it, but maybe C is not yet ready to receive it. So will ready I, using this statement, will ready I be high if B is ready but C is not? Yes, so actually this ready will be high, but will that mean now that both B and C will then receive that valid data?
No.
It actually won't, right? Because both B and C need to be ready. So actually you don't want to say that A is ready to like send out the data if one or the other is true. Instead, we want to make sure that it's only true if both of them are ready. Like that. Yeah. Okay, cool. And then how do we connect our valid signals? Yeah, I think we could probably just connect it. Right, yeah. So something like this, except instead of A ready I, it'll be, I guess, B and C valid. Okay, let's see. So this will be B valid, or that's okay. B valid is equal to A valid. Yep. Excellent. So therefore, yeah, so if we have maybe like a longer chain of this or something, or if we have now like a more of just like a linked list structure again, where we have like a single row consumers and producers, as opposed to like a tree structure like this, then if we have like this structure and we have this structure, like depending on if it's like tree going in like this or a tree coming out like this, in that case, will there be like proper like backwards propagation of the ready signal? Yes. So as long as we connect our modules like in this style, then like this is the proper way. If we wanted to have like a tree of data, at any point. Cool. This is something that like I use all the time. Like oftentimes when I'm connecting a bunch of ready valid interfaces, the only combinational block that I have is basically just a big thing to assign all of my like readies and valids and like routing the correct thing into the correct module. Yeah. Yeah. All right.
What about for like the first example?
Mm-hmm. Yeah.
So like
This one?
yeah, let's say we're like in a GPU or something.
Yes.
We have multiple different matrix operations being done.
Yes.
In each one of like A and B. So something like this here would be done for like each matrix operation module.
Mm-hmm.
Separate, and then have a ready valid kind of interface.
Mhm.
And then it finally sends out alpha.
Yeah.
Okay.
Sure. Yeah, absolutely. Cool. Another thing that you may want at some point, though, is actually maybe you have some sort of structure like this, and depending on your output, you might want to route it to one destination or the other. A common example may be like instructions. Like maybe this somehow is like your instruction decode stage. And so you've now properly taken in an instruction, maybe it's taken a few cycles, but you finally decoded this instruction, and you've realized, oh great, I need to send this instruction to my matrix multiplication unit on chip. Or maybe I need to send this to my ALU or something. And so maybe you have like all of your data lines hooked up everywhere. Like maybe you have like another thing down here, and actually I will make another slide. Okay. Yeah, maybe you have another one down here. Do this. Okay. Question is, how do we now route this out? If maybe we want to now select one of them to receive the data, as opposed to all of them receiving the data. Okay, go and write it out if you haven't already. Write out exactly what this would look like. So now we're going to have, we can just ignore D for now, as we're writing out the like Verilog for it. But what would the Verilog look like for the connection between like, yeah, A to B and C? And maybe assume that there's some like internal thing inside of A that says like data to be sent to B or data to be sent to C. I'll call it maybe select. Yeah, maybe this is like a enumeration thing where you can just say like if select equals B or if select equals C. Okay, yeah, how would this look? Okay, I'm getting some good eye contact already, so I'm assuming people already have an idea. Can I get a thumbs up if you like know exactly what line of Verilog to write here? Okay, also, maybe like, one of these, medium, okay, all right. Yeah, discuss for a little bit. I think this is a cool problem. So yeah, discuss like how'd you go about this? How could you route out which destination to go to using Verilog?
Right. Trying to figure it out. Get mad at C.
I think, well, let's just say like, you only have like B and C.
Right.
You could use like, if a valid of,
I guess if you
And-
select, or just select A.
oh, yeah.
Because I feel like once you choose which one to go, then you can put it through the ready valid stuff for that path pretty easily.
Mhm. What is select again?
Select, I think, tells you which one A is trying to send to.
Okay.
So like if we have that, instead of just like a standard, whichever one's ready or round robin type of thing. This messes with my head because we're doing the same exact stuff in Chisel in 228. I'm like, oh, you call the arbiter library. There is no arbiter library in Verilog. And then I'm writing Chisel with semicolons, and I look like a crazy person.
That sounds like a really fun class, actually.
It's a friend class.
Is Scott teaching that this
Yeah.
quarter? I didn't know he was teaching this quarter.
Skibidi Scott, yeah.
Isn't that like this baby, that class?
The class, oh yeah.
Like that's his personal class, like 2 days ago.
Exactly, yeah. It's available online if you ever want to just go through
Yeah,
it here.
no,
It's
Neil
open
was
source.
telling me about it. I wanted to take it, but.
I heard he's not teaching anymore, like next year.
Really?
Yeah, that's what I heard.
I mean, it's open, it's 228.
228.
It's available open source online.
Like Anna's YouTube channel, I can find lectures.
I read it.
So you're saying I didn't have to pay all this money to take that class?
And now you're not taking that class.
Yes.
right?
I mean, so you're saying if it's online, I don't have to be here in college?
Okay, so what do we put for A ready? Yes.
I was thinking of demugs.
Okay, a DEMA, or sure, can you write out, or can you tell me what to write out here?
No.
Okay. Maybe someone else? Yes? Not? Or, okay, Ella? Yeah.
Would you do like a ternary operator?
Oh, sure, okay. So what would this select be?
So the select, so A ready O would be select maybe question mark. Or I guess if in just a 2-bit BC thing, you could assume that it's like enumerated, so 1 is B and 0 is C or something.
Okay, sure. I guess it was kind of a bad question. So let's say, I'll actually give it to you. So let's say select equals, yeah, let's assume it's an enumeration, so there we go. So select equals B. So if we are currently selecting B, then what should happen?
Should be high. I don't know.
Then you should, A ready O should be ready I, B's ready I.
Yeah, B ready I, okay. And I'll just do B R I, just to shorten it, okay? Now, let's say, yeah, now we need to worry about like what happens next. So maybe we can say, and bring it down to another line. Yeah, we can kind of nest it. Maybe a little gross, but it'll be all okay, I promise. So now we say, well, if we're selecting C, then now we'll do this. And so what if we're now selecting C? What should the new output be?
C ready I.
Yeah, so C ready I, okay? Maybe otherwise, we just say it is an unknown value. So we can just say 1 apostrophe BX. And,
Not 0?
yeah, because like we could do 0. Oh, you know what? No, that makes more sense. Yeah, we should probably do 0. Thank you.
What does a J mean?
It is a semicolon that I will actually just get rid of.
Oh.
Cool, okay, yeah.
Sorry, can you scroll up to the earlier example? You had,
Yeah,
yeah, okay, but you had.
Did I mess up?
Yeah, it should be ready I for A, if you go down back down.
Yes.
I was wondering.
Wait, which one is
Like,
which?
go back, go back. Down,
The one you just did, you had A ready O.
Yeah, it should be ready I and then the.
Thank you.
The other one should be ready O.
But it's like related to ready C12, right?
Yeah.
You are completely right, yeah.
That's
Thank
all.
you very
That's
much.
confusing.
Yes, yep, thank you. Does that make sense? Yeah, because the input to I's is coming in this way from the outputs here. Yep, thank you. Good, okay. And we could probably imagine something very similar is happening with a valid. Now, we can probably just this, and then we'll probably just change all these to now say valid, all right? Is that fine?
Should be valid output.
My,
A valid output.
Yeah.
oh, you know what? I don't know what I'm doing. No, you're totally
Yeah, I
right.
think, I don't know, just.
Sorry, I got excited. Yeah, hold on. So this is,
Are we trying to select which of the B and C we're sending data to?
good job. Okay, so yeah, no, you're right. So we have B, so if we have B valid I, yes, thank you. So if we have B valid I, the question is when do we set this to 1? And we set it to 1, I guess, when, yeah, so when select B is activated and then we grab A dot valid. Otherwise, we would grab probably 0. Yeah, thank you. And then something very similar for C, where it's just select equals C, and then C dot valid. Yeah, cool. Okay. Can we do better? There is a way we can simplify this just a hair.
Case statement?
So a case statement will actually
On
exactly
some-
create this.
Yeah.
Like it'll synthesize to the same thing. I guess, is there a way to write the code such that it will produce a more simplified circuit? This will work, but we can sometimes do better, especially if we have like a bunch of modules here. Because putting muxes, honestly, muxes are a little bit slow. They're not terrible, but like we can do better. Yeah, oh, wait, okay, speak together for like 30 seconds.
I maybe a little bit.
Could you send the both of them to 0 first and then only send them if select equals corresponding? Although that might just.
That would probably be a must.
I think that's what he's in.
My thoughts are lookup tables, but that might just because that's what this lab is about.
Oh, is it actually?
The first part of it is lookup tables, but that's also fresh on my mind, so that might be a straight guess.
That pretty much has like a true table. Yeah, we know.
How would you use a lookup table?
You could,
Oh, nice.
I guess these are modules, so I don't remember yet, just my brain's
Built-in BNC for
Uh,
MacBooks, it saves your.
But I guess you could store each of these things in the lookup table.
Okay.
Store the ready bits there.
So, assuming what you assume, you can simplify this a little bit. Yeah, anyone have an idea? Okay, yeah. What was that?
Lookup table?
I'm not sure how we could utilize that. Can you walk me through it?
Yeah, so we have a true table with the multiplexer, so we can set the LUT initializer to whatever the multiplexer output would be.
So, the thing about lookup tables is that you hard code the values, because yeah, lookup tables are basically just multiplexers where you have a select like address bit, but then when you grab out that data, it won't, yeah, like the data in it is hard-coded. So I don't really see a way that we can use a lookup table for this. I guess maybe we could use like one of these as like a selector as well, but I'm not seeing a way. I think we can do even better. Yeah,
I don't know if this is efficient for like larger ones, but you could rewrite your mux in terms of aggregates.
okay, oh, absolutely, yeah. So that's definitely an optimization. So if we look right here, if we say select equals v is 1, then we will grab this case. That's the same thing actually as, I'm gonna make a slide, and I'll publish these slides because I think will be useful. We can probably simplify this if instead we just make this be an AND gate. And so now this is no longer going to be a mux. Now it's going to be an AND gate. Okay. I'll give you a secret though, that actually writing our Verilog this way and writing our Verilog with the mux this way actually will not change the synthesis output. Our tools will just automatically go and perform this optimization for us. It'll just automatically convert into an AND gate. This actually won't save any logic. Yeah.
How does the optimization work? Does it just create like some kind of truth table and it just chooses the...
That's exactly right. Yeah, so muxes just in general, when it sees this structure, it just knows that this is an AND gate. This is just like, yeah, it just knows this is an AND gate. You can also do the same with a mux, where, I can't say it off the top of my head, but there is, sorry, not the mux, a OR gate. There's a way that you could say like, might be just if you set this to a 1. Is that right? This is 1. I don't know, there's some way you can
I think, yeah.
optimize it. Yeah, to a OR gate, yeah. Okay. Is there a way we can actually simplify our logic? Specifically, right here. The optimizations. Well, yeah, so like I said, so this requires a little bit of assumption in your design. But what we could probably do is instead of these selects right here, we might be able to just say, if everything is ready to receive, then we no longer need this mux right here. So we can just actually AND these readies together again. We can just say like, oh, if this is ready to receive and this is ready to receive, well then we know then we're okay to send the data because at least one of them will be happy to receive the data.
Isn't that what we did
Yeah.
before?
That is what we did before. Yeah.
And did we find impractical?
What was it?
Never mind. But didn't we make it into an AND because we found it impractical? Actually, I never.
So we let me write it out. Yeah, so we can just AND together B ready and C ready. Potentially, but this requires an assumption. Okay, maybe absorb for a second. Come up with an edge case where this will not work, and then come up with like a case where it does work. But yeah, first there's a question.
Wouldn't this slow it down? Because like, if our intention is for A to be ready when either B or C is ready, then wouldn't this defeat the purpose of that?
Oh sure, you're saying that now we're going to like stall more often?
Yeah.
Absolutely, yeah. But that's assuming that we are going to have the case where maybe one of them is like, maybe we have, that's assuming the case where we have multiple of them that are actually expecting data. Like we may instead just assume that only one of them can work at one time. Like we may assume that it's impossible for two things to be working in parallel. And instead, yeah. What was that?
So we'd rather optimize the circuit than the ready validated results?
Well here, right, because, so in designs, like your stages, remember your pipeline stages, like the goal of pipeline staging is to increase your clock frequency. And remember, so for this case, if we had like 20 modules here that we needed to choose between, and we had this huge mux tree, like a 20 input mux tree could actually be so slow that we would need to lower our clock frequency. And so in that case, it may be better to either, I guess, put another pipeline stage in the middle of our mux tree, or what we could do is just say, you know what, like each one of these can only be like active at one time, so therefore we'll just AND all these ready signals together and that'll work instead. Yeah, okay, go and ponder this, see if you can explain to the person next to you why this will work, and specifically like in what case this will work.
It won't work in both.
Okay, picture this, right? Maybe A has just processed something and now it wants to send it to B. Okay, so A processed it, sent it over to B. Well, first it's like, okay, is B ready to receive data? Let's assume it is. Is C ready to receive data? Let's assume it is. So both B and C are ready to receive data. So A is going to be, like, it sees that this interface is ready. Then if it is trying to send to B, then maybe it will also set like this select enum to B. So in that case, C valid will be set to 0 here because we have this select equals C, but we're assuming that select is equal to B in this case. So okay, so therefore this C valid will be 0. It will be ready, but the valid will be 0. And then B valid will be true because it will see that A valid is true and it will see that select is B. So therefore, yeah, B will properly receive the input. And then let's say it processes it, it's done, and then it sends it over to the next stage. And now B once again becomes ready to receive data from A. So therefore, yeah, that is an example in which it will work. Okay. Could anyone tell me an example in which this will not work? First, did you have a comment?
I have a question.
Yeah.
For this select B, are you just putting like B ready, or B is ready to like receive it, so like B ready and
Select is just which one I want to send it to.
but then like where do we get that?
Yeah, I'm just saying that like maybe A produces that. Like maybe A is like our decode. Maybe select like is the data, is a part of like the data package that it's sending.
Okay, then like how does A know which one is ready first?
Well, yeah, it doesn't need to know which one is ready first. It just needs to know like, is everything ready potentially? You can think of it like if everyone in this room right now was maybe ready to receive like I don't know, a homework problem from me, but maybe I only need one single person to actually do the homework problem, and maybe I don't know who's responsible for which like homework problem. So I say like, okay, are you all ready to receive a homework problem? And you're all like, yes, we're ready to receive. It's like, okay. Then I pull out like a hard pure math question. I'm like, okay, here you go. And you all collectively are like, oh, okay, great. This one pure math question, this is going to Joanne, and I don't need to know. I didn't need to know exactly what like Joanne's expertise was. Like I didn't need to know like which output I guess like I was even sending it to. I'm just saying like I'm sending out this data, and are all of you ready to receive the data just in case you are the one to receive that data. So therefore, I'm just asking like, is everything potentially ready to receive the data, just on the off chance that you are the thing to actually process it?
Okay, so does it cycle through every single thing? Like
You would just and like all of the possibilities in this ready signal. So this then would also be like and D or something.
well, yeah, I get that. I'm still
Okay.
confused about like the B valid and C valid.
Okay. Yeah, so this is just, you can think of this as like, if Juan is expecting, like it's waiting, Juan is like waiting for select to equal pure math. And when finally select equals pure math, and there is a valid homework assignment, then he will go and do the assignment.
But like the select is done by A. Like it chooses which to select.
Well, there's only one data that's being produced. The data is just being produced by A.
But then you said select B would also be produced by A.
Select is also produced by A, yeah.
So does that mean it chooses who to give it to, or?
Right, so A will choose who to give it to, yeah. But it won't choose specifically in this,
When
it won't look at which thing is actually ready to receive. It'll check, like, is everything ready to receive?
Yeah, but like, depending on how you implement the select bit, is
Yeah.
that just inefficient unless you know like what's ready and like what's not ready?
So this will be more efficient because there are fewer logic gates, and so there's less logic. There is a chance that maybe there's less parallelism that can happen, But sometimes you don't necessarily care about that because sometimes these modules will just act completely disjointly from each other.
Wait, so then, like, if you wanted to run as maximally parallel as like possible,
Okay.
would you just make it all the selects one for the P valid and C valid?
Well, if you wanted to run like in as parallel as possible, then you might need to go back to this design. But this implementation right here is just going to be a little bit larger, and this may end up slowing down your design. If you imagine now you have like select equals D, select equals E, select equals that.
Okay. I think I get it.
Okay, sure. Do you have a clarification?
No.
Okay. Okay. I think that's probably a good enough place to end unless there's any more questions.